Okay, now let's continue discussion of convergence and divergence of the series. And for the first time, maybe in this lecture, I'm going to give you the example of a theorem that you have not seen before. It is really a remarkable theorem, and I'm going to prove it to you. So the theorem goes as follows. Let sum of ak, well, k this time will go from 1 to infinity, just because it's a little bit more convenient. It's really relevant. Be series with positive terms. But not only the terms are positive, the terms are all the terms, not the partial sums, but the terms of the series are also decreasing. So a1 will be greater or equal than a2, will be greater or equal than a3, greater or equal, etc. So of course, the only interesting case is when the terms of the series go to 0, and we try to decide if the series converge or diverge. So the theorem says that the series converges if and only if the following series n from let's see, n from, I don't know, 1 to infinity of 2 to the power n, a sub 2 to the power n converges. Okay, in other words, what I want to do is I want to take just some of the AA's, very, very few of them, A with a subscript 2 to the n, multiplied by 2 to the n, and look at the convergence of this series. And if this series converge, then the original series converge. If this series diverge, then the original series diverge. So again, just to write it down, what I mean, I have the series that look like this: a1 plus a2 plus a3 plus a4 plus a5, and I'm sorry, I'm going to write quite a few of those terms, plus a6 plus a7 plus a8 plus a9 plus a10 plus a11 plus a12 plus a13 plus a14 plus a15 plus a16 plus etc. So this is a series of a's, and what I'm going to do is I'm going to take, well, if n is equal to 1, then I'm going to take 2a2, right? And if n is equal to 2, then I will have plus 4a4, and if n is equal to 3, I will have plus 8 sub 8, and if n is equal to 4, I will have plus 16 a sub 16 plus etc. And I'm going to compare the series in the top and the series in the bottom, and I will say that the series in the top converges if and only if the series on the bottom converges. Okay? Okay, so let me not rewrite this thing, and I'm going to try to indicate the proof of this theorem, and then I'm going to do some applications of this series. So again, let's take this terms over here, a1, I'm going to write it down again, a1 plus a2 plus a3 plus a4 plus a5 plus a6 plus a7 plus a8 plus a9 plus a10 plus a11 plus a12 plus a13 plus a14 plus a15 plus a16 plus etc. And next what I'm going to do is I'm going to put some brackets around it in a very, very particular way. So in a way I'm going to put it first is I'm going to say, let's look at these terms which you call a1 plus a2. Right? Maybe I shouldn't have done that. Okay, so let's look at a1 plus a2 plus a3. Now notice that a3 is less or equal than a2. which means that A3 plus A2 is less or equal than A2 plus A2, which is equal to 2A2, right? So what I can say is that this particular term is less or equal than 2A2. Now let me look at the next terms. Where did we start? A4 plus A5 plus A6 plus A7, right? A5 is less or equal than A4, A6 is less or equal than A4, A7 is less or equal than A4. So this term is less or equal than 4A4. Let's do it one more time. I'm going to look at the terms A8 up to A15. And now how many terms do I have here? 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 terms. And each one of those terms is less or equal than A8. So this is less or equal than 8A8. And I'm going to continue in this way. In other words, now I can say that the partial sums of this series, so for instance the partial sum S15 is less or equal than A1 plus 2A2 plus 4A4 plus 8A8. And of course the same way I can conclude that A sub, what is the next one? 16, 32, 31. A sub 31 is less or equal than A1 plus 2A2 plus 4A4 plus 8A sub 8 plus 30 plus 16 A sub 16, okay, etc. So my conclusion is that if this series converges, it means that the partial sums of this series are bounded, the partial sums of this series are bounded, and that means that the partial sums of my original series are bounded. And so what we conclude is, if this series converges 2 to the n, A sub 2 to the n, then this series converges. Now the next step in this journey is to do it the other way around. So once again I'm going to take the same series, so let me rewrite it one more time. It is, if I am right, and I'm sure I am, it is A1 plus A2 plus A3 plus A4 plus A5 plus A6 plus A7 plus A8 plus A9 plus A10 plus A11 plus A12 plus A13 plus A14 plus A15 plus A16. And this time I'm going to break my sums a little bit differently. I'm going to take A1 plus A2 just as they are, and then I'm going to take A3 plus A4. So now notice that this is greater or equal than 2A4. Agree? And these guys plus A sub 8. So this time I'm including the endpoints. This is greater or equal than 4A sub 8. Well, A sub 8 is the least number of this 4, so it's greater or equal than 4A4. And finally I'm going to go this way, and this will be greater or equal than 8A sub 16. Okay. So my point is that the partial sum of the series AK is greater or equal than the partial sums of the series sum of 2 to the n minus 1 A sub 2 to the n. So does this n minus 1 bothers you at all? Well, it shouldn't, because this 2 to the n minus 1 is the same thing as 1/2 times the sum of 2 to the n A sub 2 to the n. Okay, so the point is that if this series diverges, this series diverges, and if this series converges, then this series converges. And this is a remarkable theorem, and let's do a few applications of this theorem very, very quickly. So the theorem you probably have not seen before, but the applications of the series you have, you probably studied it in Calculus 2, you studied it in a somewhat different format, but let me look at the series sum of 1 over k, k from 1 to infinity, so this will be 1 plus 1/2 plus 1/3 plus 1/4 plus etc. Okay, and you probably remember from Calculus 2 that the series diverges, but this time I'm going to prove that the series diverges using the theorem that I proved just a minute ago. So my terms here, ak, is equal to 1 over k. Good. So what is a sub 2 to the k? Well, this is equal to 1 over 2 to the k. Okay? So if I am going to take 2 to the k, or 2 to the n times a sub 2 to the n, it will be 2 to the n divided by 2 to the n. It's going to be equal to 1. And so this series, 2 to the n, a sub 2 to the n, is equal to the sum of ones, and we know that the series diverges because the terms of the series, the sum of ones, do not tend to 0. Now, on the other hand, let me try, for instance, the sum of 1 over k squared. And again, you probably know from Calculus 2 that this series converges, and this time we are going to deduce it from the theorem that we just proved. So in this case, my terms, an, is equal to 1 over n squared. So a sub 2 to the n is equal to 1 over 2 to the n squared. And if I take 2 to the n times a sub 2 to the n, I will have 2 to the n divided by 2 to the n squared, which is equal to 1 over 2 to the n. And so what about the series 2 to the n a sub 2 to the n? Well, this is a series 1 over 2 to the n, which is the series 1/2 to the power n. And as you recall, this is a geometric series, and this x over here, which is equal to 1/2, is less than 1, and therefore this series converges. Okay, so this is just a way of showing you something that you studied in Calculus 2, but in a completely different way. Let me say that there are two reasons why this way is better, but reason number one is, remember, in this course we only deal with things that we defined. We never deal with anything that we have not defined. We never defined integrals, we never defined logarithms, and so it would be out of the question for me to use some sort of an integral test of convergence here, because we never dealt with integrals. Well, let's do it a little bit more general. Suppose that I have a series 1 over k to the power p, where p is a positive number. So if p is a negative number, now let me write it bigger, sum of 1 over k to the p. If p is a negative number, of course 1 over k to the p would diverge, because the terms would converge to infinity and everything else is out of the question. And let me try to use the test that I just used. So my terms here, a sub n, is equal to 1 over n to the power p. So a sub 2 to the n is equal to 1 over 2 to the n to the power p. And so 2 to the n times a sub 2 to the n is equal to 2 to the n divided by 2 to the n to the power p. You're good in it. Okay, so if p is less or equal than 1, then this 2 to the n, a to 2 to the n do not converge to 0, and so the series diverge. And if p is greater than 1, then 2 to the n divided by 2 to the n to the power p, it's equal to 2 to the n divided by 2 to the n times p, agree, which is equal to 1 over 2 to the n p minus 1, and remember p here is greater than 1, so it will be equal to 1 over 2 to the p minus 1 to the power n. Now once again, if you think of this as x, this x over here, if p minus 1 is positive, this x is strictly less than 1, and the conclusion is that the sum of 1 over n to the power of p converges. If and only if p is greater than 1. So if you took some Calculus 2 class, and if you remember this class very well, you will probably remember that these are a particular series which are called p-series or p-criteria of convergence or whatever else they called, but we just deduced it from using that beautiful theorem that I proved a minute ago. Let me say a few more words about it, just out of curiosity, although I will not be giving any proofs here, because again, if I try to give proofs, they would involve integrals and logarithms, and I'm not allowed to do it by condition of the course. But here is the thing. Okay, the thing is that if I look, for instance, at the series 1 over n to the power of 1, then the series diverge, right? If I look at the series sum of 1 over n to the power 1, 0.001, so this time my p is equal to 1.0001, and this time the series converge. And of course, if I look at the series sum of 1 over n to the power 1.00000001, then this number is still greater or equal than 1, and the series converge. Now also notice that when I talk about convergence or divergence of the series, never ever ever do I dream of computing what it converges to. I just want to conclude if the series converge or not. Okay, so here is a question. Is it possible to write sum of 1 over something that depends on n? And that something that depends on n will tend to infinity a little bit faster than n. So phi n tends to infinity faster than n, but slower than n to any power, like 1.00001. Okay, so something, remember how I told you that in order to decide whether the series converge or diverge, we need to see if the terms converge to 0, and if they converge to 0, then the next question is how fast do they converge to 0. Well, this is fast enough. This is not fast enough. Is there something in between? And the answer is yes. And this is a series 1 over n natural log of n. And in this case, these terms converge to 0 faster than 1 over n, but slower than 1 over n to any power bigger than 1. So what about this thing? Is it converges or diverges? And it turns out that the answer is diverges. Okay. So the next question, can we make it a little bit faster so that the series would converge? Yes, we can. We can look at the series 1 over n times log of n to the power of 1 plus epsilon to a little bit bigger power. And if epsilon is bigger than 0, the series converge. Well, if you're a mathematician and if you're interested in deep learning, you will say, well, can I go on? Can I make something to converge to 0 faster than this, but slower than any one of those? And the answer is yes. The sum of 1 over n, and then I will have log of n and log of n. And this, remember, this tends to infinity, so this will converge to 0 faster than this, but slower than any one of those guys. and it turns out that this series diverge, but guess what happens? If I put a little bit bigger term here, if I change it to 1 plus epsilon, now the series would converge. So where is the dividing line between convergent and divergent series? It basically does not exist. If it exists, and if you assume that this thing exists, it would be somewhere in this place, sum of 1 over n, and then you will have log n times log of n times log of n times etc. So if you take infinitely many of those log n's, whatever that means, this is precisely the dividing line between convergent series and diverging series. Okay. So this is basically the end of the lectures for this first week of our strange teaching. Let me just finish with doing one more thing to prepare you for what's coming up. And the series that I want to look at next will be a very, very famous series, perhaps the most famous series in the history of the world, or maybe the second most famous series of the history of the world. And this is the series sum of 1 over n factorial. N goes from 0 to infinity. Is this better? No? Okay. This is good, right? So what does it mean? Well, 0 factorial is equal to 1, as you probably know. 1 factorial is equal to 1. 2 factorial is equal to 1 times 2. 3 factorial is equal to 1 times 2 times 3. 4 factorial is equal to 1 times 2 times 3 times 4, etc. n factorial is equal to 1 times 2 times 3 times all the way up to n. Okay, and so these are the bottoms, these are the denominator in my series. And my first question is, does this series converges or diverges? So let's look at this series. 1 over 0 factorial will be 1, 1 over 1 factorial will be 1, and then you will have 1 over 1 times 2, plus 1 over 1 times 2 times 3, plus 1 over 1 times 2 times 3 times 4, plus 1 over 1 times 2 times 3 times 4 times 5, plus etc. Do you agree with me? Yeah? Are we good? Okay. So let me compare it to something. 1 is equal to 1, and then I will have 1, and then I will have 1 half, right? These two terms are equal. And this term is less or equal than 1 over 2 times 2. So 1 over 2 times 3 is less or equal than 1 over 2 times 2. And the next term over here will be less or equal than 1 over 2 times 2 times 2, because 2 times 3 times 4 is bigger than 2 times 2 times 2, so 1 over it will be less. And the next term, of course, will be less or equal than 1 or 2 times 2 times 2 times 2. In other words, what I'm doing is I'm comparing this series to the series 1 over 2 to the power n, well, plus 1. And here goes from 0 to infinity. And once again, this is geometric series. This is a series that we were dealing with in this class. And we know that this series converges. Now, the terms of this series over here is less or equal than the terms of this series, and therefore this series 1 over n factorial, and from 0 to infinity, converges. Now I'm going to tell you a little secret, that what you know about number e is not how the number e was discovered. Once I know that this series converges, and this series is so damn important in life that we give it a name. And the name for this series is e, 1 over n factorial. So you see, Remember how I told you that I really cannot seriously define E, because E was defined to be some sort of a limit, and in order to prove that the sequence converges to some limit, I have to know the limit, but the limit is defined in terms of convergence of the series, and this is a closed circle from which there is no escape. Well, now I'm going to go with a different route, and I'm going to say that I already proved that the series converges, and whatever the number it converges to is the number I will call E. Is there a relationship to E that you know? Well, yes, there is. And the theorems that we will prove next time, together with a few other theorems, so next week, will be that if I look at this sequence, 1 plus 1 over n to the power n, so this is a sequence. This sequence converges to E, but this time I'm not violating any rules, because this time I didn't define E as a limit of the sequence, I defined E as a sum of this particular series, and now all I have to do is to prove that this sequence and the partial sums of this series converge to the same number, and therefore it's number E. So I will do it next week, and in the meantime, have a pleasant weekend, study hard. Remember that the videos that I send you, they by no means constitute everything. They just constitute the addition to the textbook. So also read the textbook, please. Thank you.